All right, welcome everybody. We are here for NASA's Universe of Learning Informal Learning Network webinar number 6, Exoplanet Detection. What can we know? This is the first of the last two of our webinars, these two focusing on Are We Alone? With you today, we have myself, Tim Rue, at the Space Telescope Science Institute, and Brandon Lawton, our education outreach specialist here. Erica Wright is on the line as well, able to answer any of your questions you might have if you put those into chat. Mary DeSalt will not likely be joining us. She had some other things going on today, but she sends her regards to all of you. And as we normally do, Natalie Wimberly is here. Hi, Natalie. Any of your affiliations questions you may have, she's your person. Also joining us today, we have Dr. Vanessa Bailey from the Jet Propulsion Lab, NASA's JPL, out in Pasadena, California. And she'll be talking to us a little bit later about some of her work in exoplanet detection and some of the exciting things that are coming up that NASA's going to be doing. So welcome to Vanessa. Today, I'm going to start off talking through some of the resources, as we always do, connecting how some of the work that we are, or how some of the science that we're going to be talking about today can be brought into your place. And then Brandon's going to talk a little bit about imagining other worlds and some of the different detection methods out here. And then we'll hand it over to Dr. Bailey to talk a little bit about her work as well. Oh, yes, and we obviously this one is going to be fitting into the other solar systems, other Earths category out there. And of course, how do we know what we know? Next week, we'll be talking a little bit more about habitability, but today is going to be more on the detection side of things. So first, the biggest resource that we need to make sure we share with you is Eyes on Exoplanets. We've mentioned this one before, and there is both a kiosk version, which is meant for museums or planetariums or science centers or whatever out there for the public to come in and start playing with this tool immediately without having much of a learning curve. And there's an online version that anybody can play with at home as well. Let me actually, I'm going to hop out of my full screen and jump to eyes.nasa.gov. The app is available for you to get in there, and you can actually open NASA app. And I might need to adjust my share here just a moment. Let me just jump to desktop 2. I'm looking off to my other one where I've got this going. And it is taking just a moment to load up. So within Eyes, we have this whole 3-dimensional place where you can go and explore the universe. You can see what the latest discoveries are in exoplanets. I'll note that the dates that you see on mine are not the most current. Eyes actually is updated on a basically daily basis, but it's possible to have an offline server-based mode, and I just have not updated the server on my computer for about 6 months. But that's useful if you need to be showing this off in places without internet access, or if you've got it out on the floor and don't have that. You still want to plug it in so you can get that updated data, but it is here. So you can see one of the most recent exoplanets back in February. All of these different planets have all sorts of information that we have actually been able to detect. This is all based on the science. This is pulling from NASA's Exoplanet Archive. Oop, let me zoom out a little bit more. We should be able to see. It's being a little bit slow. But we can see how large this thing is compared to our own solar system. This is one with actually 2 planets going around it. We could check out either of them. You can get information on how far away these things are, both by car, by bullet train, jet, light speed. That's a distant planet. You can see where the habitable zone around this system is. So you can see these ones are a little bit close in for liquid water to be hanging around. These planets are far inside of this shaded section. But there are all sorts of different ways to go through this. You can look at all the discoveries that Kepler has made and pick on any of them and go check it out. So we'll fly into this particular one. We'll talk a little bit more about Kepler and TESS as we go through the webinar later today. Brandon will mention them. But basically every exoplanet that's been discovered is in here and you can go explore. It's a really fun thing. The kiosk mode is set up very nicely as well so that you can just check out the weirdest planets, or you can check out with a view from where you are actually located of the night sky and where all those exoplanets are in the sky. It's really easy to jump in. You don't have to play around too much. So let me close that down. Yes, I do want to quit. And I will jump back to my webinar. And give me one moment. I just need to grab my notes. And go back to full screen. All right. So eyes on exoplanets, really amazing application. If you haven't pulled it, go ahead. It's free. Check it out, play around, and you can explore some of the things that you're seeing and hearing today and figure out how you might be able to incorporate this into an activity or a program or something else, or an exhibit. But the next thing I want to mention is DIY Planet Search, which is a NASA-funded interface to the Micro Observatory Robotic Telescope Network. So we've mentioned Micro Observatory a bit before, but with DIY Planet Search, anybody who creates an account on here can use one of those telescopes in Arizona to actually detect recently discovered exoplanets yourself, just about every night of the year, as long as the weather is clear enough for it. Those telescopes will go and measure the brightness of a star, and they look at, they're set up to look at ones that we know exoplanets are there, but you can get completely new data and analyze that yourself and be able to detect the exoplanet orbiting. And you just go to the same site as Micro Observatory, microobservatory.org, and then down here on the bottom right, you'll see a DIY Planet Search. Open that up, and you can go in and create your own account and get access to this. But this is actual data here, pictured on the left, that was captured by Micro Observatory, that shows where an exoplanet detection would be. Next up, our virtual reality stuff. So JPL put out some 360-degree images of what it would be like to stand on the surface of a couple different exoplanets and one fictional exoplanet moon. We know the exoplanet is there, but if there was a moon going around it, they put they'd show you what it would look like to be there, because the planet is a gas giant and you can't actually stand on that one. And there's a little bit of information, but you can look at this with something like Google Cardboard. You can actually pull this up through YouTube as well, and the 360 view that YouTube has. I do recommend Cardboard or a phone if you can, but you can just look around and see some of the really cool stuff. We'll visit this again next week. There's some other cool virtual reality stuff out there that NASA sites have put together. I also need to mention the rest of exoplanets.nasa.gov, which has all sorts of things like some detection animations, which we'll be looking at during the webinar today. Brandon will show some of those off. And then there are some activities where you can make your own planet and more. You can see Extreme Planet Makeover here, an Alien Safari. But those are all on the site listed here. And as always, we'll have the slides up so you can follow those links later. Also, one more universe discovery guide I'm going to mention. This one, we've mentioned those discovery guides the past couple of weeks. April has a issue focused right on discovering exoplanets. So that's a good one to check out. The website is there as well. Also, we recently put together a coronography activity. Brandon will be talking about coronography a little bit later. This was a pilot activity that we tested. We haven't actually run this ourselves with an actual audience, but maybe you're interested in doing something like this or modifying it. If you've got some questions about this activity, if you want to try it out, if you want to change it up, please do so. We want to know what happens with that. And the last thing I'm going to mention before we pass this over to Brandon is a fun human-powered orrery activity. So an orrery is a device that shows the motions of the planets around a star. Normally our solar system, because that's what people have been familiar with up until, 20 years ago or so. But this gives some directions for how you can create that with actual people and make a kinesthetic activity where people can move around and get a better sense of what is going on here. And I believe we had someone who did something with this with one of the previous runs through this, and we'll make sure that that activity gets up on the Moodle as well. So with that, I'm going to pass this over to Brandon. And you're going to take over the screen yourself?
Yep.
Okay.
Let me see, screen, share. Okay. And present. Okay. And you can hear me okay? All right, great. Okay. So Dr. Bailey is going to talk about some recent and upcoming wonderful science around detecting exoplanets. But we wanted to set the stage for you, if you will, with this idea that for millennia, humans have been imagining what other worlds might be. They've been looking out in the night sky and wondering, you know, what is out there? Might there be other things out there? This, are we alone in the universe, this fundamental question that NASA astrophysics is addressing, and hopefully maybe someday we'll be able to answer, is, again, something that's an innate question in humanity going back centuries. And so it's a really fundamental question that NASA takes very seriously, and we have missions that, you know, astrophysics missions that are exploring this. Giordano Bruno in the 16th century was imagining other worlds, writing, "In space there are countless constellations, suns, and planets. We see only the suns because they give light. The planets remain invisible, for they are small and dark. There are also numberless Earths circling around their suns." It's amazing to think about the idea that some of our scientific, you know, forefathers and foremothers in history have been thinking about this since, when you think about it, we've only actually proven that there are other planets out there outside of our solar system in the last 30 years or so. So this is really a new field, but it's a field that has people have been thinking about, again, for many centuries. So this is from 1686, a drawing of Plurality of Worlds. And so you can see the idea of postulating other worlds out there in the cosmos. Let me go ahead. Okay, so we're contemplating this. Okay, so what's next? What are we doing? All right, so we'll just give the punchline right up front, just so you have this. All right, so now we know, just in the last roughly 30 years or so, almost 30 years, we now know of over 3,800 confirmed exoplanets discovered in more than 2,800 star systems. On average, and this is something we'll talk about, this is something that the Kepler mission has done for us, is provide these averages. On average, there is a planet for every star, and 1 in 6 on average has an Earth-sized planet. I will allude to this a little bit later. These numbers, I believe we pulled yesterday. We pulled these numbers. They're already out of date. This is a field that is so fast. There's so many discoveries happening that these numbers are growing by leaps and bounds, and we'll get into that. Okay, it's fun to think about other worlds are not like ours, and in fact, the exoplanets that we have been discovering, the planets around other stars, a lot of them are, most of them are most certainly not like ours. We find planets that are close to their sun that are Jupiter mass or even heavier. We find planets far away. We find a whole variety of planets around that exist around other stars. So this idea that we could simply infer planet formation process and what planets look like just by our own solar system is not quite correct, although looking at our solar system is helpful. But we're really seeing that there's a large variety of types of planets out there. And in fact, whole classes of planets that we don't even see an example of in our own solar system, things called super Earths, which we don't have in our own solar system. And we'll talk about that. All right, but first, I wanted to highlight this resource that you will find on the Exoplanet Exploration website out of NASA's Jet Propulsion Laboratory. This is a wonderful interactive. This shows you the 5 primary methods by which astronomers detect planets. So if you recall, there's two fundamental questions here that astronomers are kind of dealing with. Are they out there? How do you find them? The detection question. You know, first, to be able to study them, you have to find them, right? So today's webinar is mostly about detection. How do we find the exoplanets? In 2 weeks, our last webinar will be more about characterizing exoplanets. Once you find them, what can you learn about them? And are they habitable? What other features might they have, and so on? This website here that you see is great at getting at detections. I am going to see, can you see it? Okay. Okay, I am going to show you, if you go to this website, which I'm on now, I'm going to actually just bring up 2 of the examples, but you can play with all of them yourself. So for the first one I'm going to do is the searching for shadows, this transit method. Nearly 3,000 planets have been discovered with this method. And here's a single planet going around a star, and we can't see the planet itself because it's too small and it's blinded by the starlight. But if you look at it face on the bottom left, you see a plot of the light from the star, and you'll see that it dips slightly, and that is actually very slightly. It's like something like less than 1% of the starlight. It dips slightly because the planet blocks that light. And so astronomers can look at stars over many years, looking to see if they slightly dim. And if it's a repeated pattern, they can then infer things about an exoplanet going around that star. On this interactive, you can play with different things. You can play with different planet sizes. So you can see with a big planet how much more of the light will be dimmed relative to a small planet. So there you see the dip. Okay, and then we have discovered multiple planets around systems. So you could see, you can imagine that it gets quite complicated actually in practice when astronomers are trying to do this, if they see, because you're looking for very small signatures in these dips. The graph on the lower left makes it look very clean and obvious. The actual signatures that you're looking for are very difficult to pull out. It takes very sophisticated techniques and observations to get these. But even in this beautiful case on the lower left, you can see that there could be some confusion when they overlap, the planets overlap when they cross the star and so on. So this is a great area of study. This is how most of the exoplanets that we've come to know have been discovered by this transit technique. And we'll talk about the Kepler Space Telescope, that telescope that for many years has been accumulating these transits and found a bulk of the exoplanets we know. That's been the primary mission for discovering exoplanets using this transit technique. And now we have another mission, which we'll talk about as well, called TESS, which is up and taking data from the same technique. Okay, let me see, how do I get back? Actually, I'll just go forward here and let me see. Let's do, the only other one I'm going to show, this is actually a very complicated one. This is called gravitational lensing. And this technique is going to be very important, particularly for future missions, and I believe Dr. Bailey will talk more about this. But I'll just give you this idea in which anything with mass can bend space-time. So you see that grid-like pattern, that's space itself. That's the fabric of space-time. And it'll just keep playing over and over again. And so anything with mass will bend space-time. Like you see the star bends space-time and the light comes out from the star. There's another star passing in front of that background star with a little planet going by. Okay, you can't see that planet directly again because it's too faint. But if you look in the lower right, what you'll notice is that plot in the lower right, and it'll start over again. That plot is a plot of the light that we see from that background star. You don't necessarily see much of the foreground star that's passing in front or the planet, but you'll notice that the background star brightens because it's being lensed. The light rays from the background star are being redirected and come towards us. It's called gravitational lensing. It's like a lensing effect. It's being redirected and comes towards us, and it brightens that background star. The amount of brightening of that background star, you see the light rays bending as they bend and come towards us. The amount of brightening of that background star tells us something about the mass of the foreground star. And you'll notice what's interesting here, the key to this is most of that increase of light on that plot that you see in the lower right is from that foreground star bending spacetime. You'll see a tiny little dip right about there. That little tiny dip, that added extra bump, is from the planet itself that's also lensing. It's also bending spacetime very slightly. And just from that little blip, we can infer that there's a planet there. And this is called microlensing, gravitational microlensing. And this is an interesting way. The transit technique is very good at finding planets that are, relatively close to its parent star and will undergo many transits over time because it's close, so it's traveling faster. The microlensing technique is really great at capturing the existence of planets that might be farther away from their host star. Okay, so just to give you an idea, these different techniques have different sort of pros and cons, different ways to get you different information about the planets. So using them together gives us a better census of the types of planets out there in the universe. All right, I won't go into the other examples. You can play with that yourself, and I encourage you to do so, but there are other examples of finding exoplanets. But let's get back to the presentation. Okay. Cumulative detections per year. You'll notice that, so this is cumulative, so basically every year they add on the new detections to the previous year, and that's why it goes up like this. And this is color-coded based off of the way that the exoplanets were detected. And I believe this was updated as of November 8th of this year. And you'll notice a big jump around 2016 and on. There's a lot of big Kepler Space Telescope releases that happened around those times where Kepler had many, many years of observations of stars. So they were able to release a bunch of exoplanets that were discovered. So a lot of this big increase, really Kepler launched, I believe, 2009, I believe it was. So really the big increase you see in the transits, that green, that really increases from year to year, the transit technique, is really mostly from the Kepler Space Telescope. And then you'll notice that the other types are there as well. I'll mention the radial velocity. You can play with that method on that interactive, the radial velocity or the wobble technique, which uses sort of gravity to detect exoplanets. That was the first way of detecting exoplanets, and that's still a good way to detect exoplanets. But the transit technique is the one that's finding the bulk of them now. And that microlensing that I showed you, that sort of complicated microlensing interactive, is in purple. There's not a lot of that happening yet, but future missions will, I think, really build on that technique. Okay. We're going to sort of breeze through these a little bit here. Let me see how much time. Okay, we're going to breeze through some of these. The radial velocity method, this is sort of the wobble method, the gravity method. I'll let you, what I'm going to do is I'm not going to go over all these in detail. I'm just going to leave these here. And if you have questions, please ask them on the Moodle. But I'm just going to stress sort of a main point for some of these. So the radial velocity method was the most successful method of detecting exoplanets until 2010. It basically looks at the Doppler shift of light as a star moves. So an exoplanet orbiting a star will actually, its gravitational pull will actually make the star wobble a little bit. And you can look at the redshift and blue shift of light from that wobble and infer an exoplanet. Okay, I'm going to go ahead and skip this only to mention that the whole point of this plot, if you get nothing from this plot, it's really that with this technique, the more time you have to observe something, the longer you have to observe something, the more you can start to probe to the smaller and smaller size exoplanet, getting down to Earth-size exoplanets, because the bigger the planet, the more it causes the star to wobble, so it produces a more obvious signature. So big planets are easier to detect in this way. Takes a lot of time to detect Earth size. All right, we mentioned, I showed you the microlensing method. I think, at least in my opinion, this is probably the most complicated method to get your mind around. But why I'm highlighting it is because it will be a big method in future missions. You'll notice from that interactive, it kind of mirrors what's up in the top right there, magnification of the background star, and you see that little blip, which tells you there is an exoplanet there as well in the foreground, or going around the foreground star that produced that microlensing. So like a lens, the gravity of a planet or star focuses light from background stars. This sort of figure here kind of just shows you what's going on, but really what you're actually looking at is that bright orange, what we call source star or background star, and you're looking to see if it's doing anything funny over time. And if you get these interesting mirrored images and increase in brightness of the light from that background star, you can infer the foreground objects that we're passing in front that cause that lensing effect from the gravity. This technique, though, you just have to be lucky to catch it, right? It's just, you're not always going to be lucky to have the line of sight and the light rays work such that you catch this. So you require a large number of background stars. But you can detect Earth-like planets and actually free-floating planets, planets that don't have a host star with them, planets that don't have any parent star. We might call those rogue exoplanets. Okay. I'm gonna just flash this on the screen and move on. I just want to show you what some of the actual data for a good detection, a really high solid detection might look like. And just note that you see the exoplanet blip there on the right, and you sort of, it balloons up in that pink box. Just know that the signal was very strong and there was very little noise in the signal, such that they were able to confirm that that was an exoplanet. But it's a very hard measurement to make. Okay. Direct imaging method, why can't we just look at the exoplanets directly with our telescopes? I alluded to this before, but we would do this all the time if it were easy, but the exoplanets are drowned out by the parent light, or by the light from the parent star. Exoplanets are much fainter than their parent star. But there are techniques like using coronagraphs, such as in this image here of the Fomalhaut system. A coronagraph is simply a physical structure that you actually put inside the telescope, where you can move that structure in front of the path of the light coming just from the star to block out the starlight, and then you'll be able to see around the star much better. It's basically the same technique if you're on a dark night and you're walking down the road and a car comes by you with its bright headlights shining in your face, and you might put your hand up to block the headlights so you can sort of see again because that light is so bright. Basically the same thing is happening here. We have these little we have these coronagraphs, these things where we can block the starlight, and it makes the surrounding area relatively brighter so you can actually see it. And in this system here, there's a little balloon and a little inset where they found what might be an exoplanet traveling around this star. And I'll mention that this coronagraph technology is a big area of technological development at NASA, and future missions will build upon this and develop more sophisticated coronagraphs so that we can do this better, so we can do this in more observations. Okay. Here's another example of a coronagraph. All right, and a lot of the techniques, I just say a lot of what the text here is just leading to is a lot of the work that's gone into this is actually in figuring out how to pick out signals from the noise in the data. All right, the transit technique, this is the one that I showed you, detects planetary companions by measuring a drop in stellar brightness as the planet occults or transits in front of the stellar disk. This again is the primary way that that we found detected exoplanets, primarily through the Kepler Space Telescope, but now that TESS, which we'll talk about, has been launched, TESS is the next one that is using this technique. Here is This one is actually not, this one is Spitzer discovery, so the Spitzer Space Telescope, of the TRAPPIST-1 exoplanets, so 7 Earth-sized worlds around the TRAPPIST-1 star. The first exoplanets detected around the star were actually detected by a ground-based telescope, the TRAPPIST-1 telescope, or the TRAPPIST telescope. And you can find these 7 Earth-sized worlds. So this was a big discovery when it was first announced in 2017, because, you know, finding one exoplanet is still a big deal around a star. Here they found 7 exoplanets, all roughly Earth-sized, many of which fall in what's called the habitable zone of that star system, where liquid water might be able to exist. So this is an exciting discovery, and there will be follow-up observations of this system for years to come. And this just shows you the Kepler has found the bulk of the exoplanets found using transit. Okay, and we'll go ahead and, okay, so we'll move on. One of the things that we have to get across, right, is that one of the foundational questions of are we alone at NASA is a real, you know, it's a really foundational question, but that's not the only question that we're trying to answer with exoplanet science, right? We're also just trying to answer questions like, how does the universe work? When stars and planets form, how do they, you know, how is it, what is the diversity of exoplanets that are formed during these processes? What are the types of exoplanets that can exist in the universe? And so just understanding not just possible Earth-sized habitable planets, but also strange Jupiter-sized super Earths, ice giants, the whole panoply of types of exoplanets. Astronomers are interested in understanding that diversity. So I just show you a quick comparison for Kepler and TESS. Kepler, the Kepler mission is now ended because it ran out of fuel, but it found a great deal of exoplanets, of course, as we've talked about. And it was really about the statistics of exoplanets in our galaxy, particularly the sort of number of Earth-sized exoplanets. TESS also will help us with statistics, but TESS is going to do something, I think, even better. Although statistics are important, it's the first step, but it's really going to open the door for characterizing exoplanets, helping us learn more about exoplanets, because the thing about TESS is it's going to find exoplanets that are, by and large, closer than the exoplanets that Kepler found. And so we'll be able to do more follow-up observations from our other telescopes. All right, so that's what this figure here shows you. So you can see sort of an artist's impression of our own Milky Way galaxy. On the left is a sort of more of a zoomed out view where we exist in our solar system. There's the sun. You see that yellow sort of ray of light going off to the left, goes out about 3,000 light years. That is the search area of the Kepler mission. So it basically stared at stars in that direction, a few 100,000 stars in that direction, and stared at it for years, stared at those stars for years. And some of those stars, you know, were close, but most of them, if you see that cone as it goes out, most of them are on the farther end, right? But if you look on the right, TESS is going to do basically an all sky or near all sky survey. That's what the red bubble around us is the TESS survey. So 200 light years, look out 200 light years roughly, but it's going to be around the whole sky, and it's going to find a lot of exoplanets that are much closer to us. And again, that's going to be great for being able to do follow-up analysis surveys of those exoplanets with future missions, you know, like the James Webb Space Telescope and so on. Potentially habitable exoplanets. This is ranked by distance. We don't know a lot of exoplanets that are nearby. These that are you know, possibly Earth-sized, potentially habitable. These are mostly it. So you can see the nearest, we do know of an exoplanet around Proxima Centauri b at 4 light years away. That's the nearest star system to us. The reason I was saying that things always change is because I just happened to be on my phone about 2 minutes before we started and noticed that there was a release. I think it was in Nature today. Maybe Dr. Bailey will know more about this than I will. I'm sure that's the case. But but there apparently was an exoplanet discovered around the second closest star system to us, the Barnard star, yeah. That's only 6 light years away from us, and it's just it might be a super Earth. It might be a very cold super Earth, but nonetheless potentially habitable at this point. But that just came out. That was just released in the press today, and that's less. Barnard star is less than 6 light years away from us, so that would be a big discovery. That is a big discovery. So I just to point that out, that these discoveries are happening all of the time, and with TESS up now, and TESS was launched in, when was TESS launched? The spring. Was it April? Yeah. TESS has been taking data for a few months now. We're going to be getting, within months probably, we'll be getting some. I don't know the answer to this, maybe Dr. Bailey does, but certainly I would say within months, certainly within a year for sure, we'll probably be getting some information from TESS about some of the initial exoplanets that are discovered. Although it does, you'd want to do, it can take years to capture some of the information on these exoplanets because you need to get enough of the transits to understand that you have actually detected an exoplanet. But just know that there's a lot of new data that's going to be coming out. We threw this in because this is from NASA's Universal Learning, and it's a brand new series of videos. So we have these series of videos that we've done over the last year or so called Universe Unplugged, but these are brand new exoplanet themed videos. I won't share it now. We probably don't. It's probably best if I don't share it now. You can, but there's the URL. We're really interested if you want to go after the webinar and watch the videos. Let us know what you think. You can certainly use these as resources as well to engage your audiences. And what's great about these Universe Unplugged videos is that they all use celebrities in them. So that also makes it kind of interesting. Okay. We threw this in here. This was based off of a scientific paper in 2015 on expected discoveries from TESS, although we'll be knowing what the actual discoveries from TESS are within the next several years. But TESS is expected to find potentially, Earth, we call these Earths, maybe approximately 70, 100, depending on what's actually out there, we might be able to find a lot of those. These things called super Earths, which fall under 1.25 to 2 Earth radii, so that's Earth radius. We might find a whole bunch of these super Earths, which we don't have examples of in our own solar system, as well as these sub-Neptunes and giants. I just want to make a point. These graphical shots here you see, of course, are artist impressions of what those exoplanets look like, but those are also pulled, the same artist impressions you'll find if you look up these exoplanets in Eyes on Exoplanets. So if you go to Eyes on Exoplanets and do a search for any of these systems, or any of the other systems that we mentioned today, you'll see that there's an artist impression of what they might look like, and you can look at these yourself. Okay, and just sort of as we close out before we turn it over to Dr. Bailey, NASA has a whole suite of exoplanet missions. So if I talked a lot about Kepler and TESS, and Dr. Bailey will tell you more about some of these missions, but just know that there's these detection missions like Kepler and TESS that are good at finding exoplanets. There are these other missions that are really good at characterizing them, looking at them and figuring out what's in their atmospheres and so on. Missions like Hubble and Spitzer and Webb are great at characterizing, and WEIRST is going to do a great deal when that's launched in the mid-2020s, a great deal of both detections and characterizing. Okay, and then just to mention briefly, after Webb, when WEIRST is launched, WEIRST is going to do a lot of that microlensing technique. So it's going to, if nothing else, this plot just shows you on the bottom how far away that planet that we expect to find is from its host star. So things that are more on the left of the plot, like the red things that Kepler found, are close to their host star. Those planets are close to the host star. Things that are more on the right, like in blue, are exoplanets that are farther from their host star. So just know that Kepler was great at finding exoplanets that are closer. WEIRST will be great at finding exoplanets that are further from their host star, or even those free-floating ones that don't have a host star. Okay. Oh, yes, our favorite figure, the methane figure. So we'll get more into this in the next webinar, but just know that, you know, when you get into characterizing exoplanets, you want to actually take a spectrum and look at what's in the spectrum of the atmospheres of those exoplanets, and what you see here is the spectrum of the Earth. You can actually learn a lot if you get a spectrum of an atmosphere of a planet. And you actually might be able to start determining its odds for habitability, and if you're really lucky, maybe it's odds even for potentially life on the planet. But that's the big goal down the road, just to put that in your mind. Okay, and now I would like to turn it over to Dr. Vanessa Bailey from the Jet Propulsion Laboratory, and she is the true expert in this area, so she will tell you more about exoplanets.
Awesome. Can you hear me? Okay, great.
Yes,
yeah, thank you for that really excellent introduction and overview of the field. And so I'm going to dive into a little bit more detail into direct imaging in particular. Let me just get set up with my slides here.
If you'd like, Dr. Bailey, also you did turn your camera off.
Oh, thanks for reminding me.
Yep.
Start my video. So yes, hello everybody. And share my screen and play. So can everybody see my screen? Excellent. Okay, so yeah, I wanted to delve into more detail, in particular into that direct imaging technique, because that's what I've spent most of my career thinking about, is how you see very faint things around very bright things in order to learn more details about particular kinds of planets. So I guess before I get into the science, just wanted to share just a little bit, very briefly, about my background. So I grew up in South Dakota, in the cornfields of the great cold north, where the skies are dark and is a good place for pondering the universe. I sort of knew I was probably going to be an astronomer, but maybe a biologist by the time I was in high school. Spent some time doing, my first research projects were actually related to soybeans, not stars. But made my way through as an undergrad at the University of Minnesota, and went through, oops, I hope you can't see those reminders for my other meetings. Went through and worked on various different astronomy projects, different fields, and didn't actually start working on exoplanets until I was in graduate school, where I went to the University of Arizona. And then I've continued my research career from there, spending some time at Stanford University. And now for about basically exactly a year now, I've been a staff scientist at the Jet Propulsion Lab, again, focusing on exoplanets and direct imaging. And when I'm not focusing on exoplanets, I love being outdoors. So part of the reason I became an astronomer was because it let me go to telescopes on tall mountains. And I like to spend time on mountains when I'm not at the telescope too. But getting back to the science, just to sort of recap what you've already heard, you know, the radial velocity and transits are really good at finding planets. They're prolific, but they're really good at finding planets close to their stars, sort of Earth separation and closer. If you want to find things more like Earth, more like Jupiter, more like you know, things in the exterior of the planetary systems, you need to turn to different complementary methods, and that's microlensing or direct imaging. And so I think in the remaining time is too much to cover both of these in great detail, so I'm going to just dive into direct imaging, but you can ask me questions about any of these later on. And then also just to re-emphasize that radial velocity and transits and microlensing are very good at finding things, not so good at characterizing them, with the exception that there are a very small number of transiting planets very close to their stars that can be characterized. But if we want to get detailed images or a detailed understanding of any particular planetary system, we need to turn to direct imaging, where we literally just take pictures. So this is an actual time-lapse movie put together by a couple colleagues of mine, Jason Wong and Christian Marois. So this is a time-lapse video of 4 planets orbiting a nearby star that we've taken over the course of almost the last decade or so. These 4 super Jupiters are orbiting very distantly from their star. So, sort of Neptune's distance and farther. And these things are multiple times Jupiter's mass. So 4 to maybe 10 times Jupiter's mass. So very unlike our own solar system, and something that we couldn't have found with transits or with radial velocity because they're so far from their star. And we also, with those other methods, can't see these planets directly. Here we can, test out, do Kepler's laws actually work? Yes, we know how the planets orbit their stars. But even better than that, we can kind of delve into detail. We can look at the composition of these planets by looking at them in multiple different wavelengths of light, taking images in multiple different colors, or taking a spectrum where we spread out the light of the planet and take many different colors of light simultaneously. We can do this now for the very hottest glowing super Jupiters. And so they're so hot that in fact they have clouds made not of sort of terrestrial gases like we think of here, but like carbon monoxide and molten rocks and molten metals actually make up their clouds. They're not cold like Jupiter is. We can today catch planets already in the active formation, and I think this is one of the very most interesting questions to me personally, is that how do planets form in planetary systems? We have a cartoon idea that we have this cloud of gas and dust that collapses down under self-gravity, and as in that collapse process, the little bit of angular momentum in that initial cloud means that that material kind of spins out into a disk around the star during the formation process. And it's within that disk that these planets form somehow, which is a very active area of research, and it would sure help if we could get some direct data or some direct images of that process. And so just within the last couple of years, we've been able to do this for the first time. So here's an actual image of one of these disks around a very young star. It's only 1 million years old or so. We're seeing it from the side, which is why it looks like an oval. And you'll notice that so we've also subtracted away the starlight and suppressed the starlight so that you can see the disk next to the star. And you'll notice there's kind of a gap. There's an inner ring and an outer ring and a gap, and you might wonder what's causing that gap. And if we zoom in even farther and use a different wavelength of light, we can discover for the first time a forming baby planet. So this is a baby super Jupiter forming in this planetary, protoplanetary disk. And there's only one other system where we've been able to make this kind of detection so far, but it's something that as we get better technology, we should be able to do for more systems. And so I think directly probing the planet formation process is really exciting to me as an area of research. As you've already mentioned, there are only a handful of directly imaged planets, and that's because it's incredibly technologically challenging. So planets are faint relative to their stars, and these planetary systems are very far away from us, so we need very sharp images to be able to see the planet next to the star. And so just to give you some analogies to think about, for the easy stuff that we do today are these hot, young, self-luminous super Jupiters. They're still hot from the formation process. They're glowing relatively brightly in the infrared, so they're only 1 million times fainter than the stars that they orbit. So that's basically a firefly and a lighthouse kind of ratio. And furthermore, of course, even the closest stars are light years away from us. And the young star forming regions are usually about 100 light years from us, the very closest ones. So close in the context of the universe, but still pretty far away. We need really sharp images to see these directly. And so if you want to put that quantitatively, we need to see planets that are less than 1/10,000th of a degree apart from their star from our perspective. And if you hold your arm out, and your pinky at arm's length is about 1 degree. So split that into 10,000 pieces, and that's 10,000th of a degree. You're trying to see the planet apart from its star that close. And so for another analogy, now you put that firefly and the lighthouse 20 feet apart, and you try to see it halfway across the country. And then you try to take a spectrum of the light of that firefly to see what it's made of. That's the easy stuff that we can do now. We do this on a variety of telescopes from the ground for the easy things. So most major telescopes now have instrumentation that's capable of doing this, but that's not a solar system twin. That's not a Jupiter analog. That's not an Earth analog, and that's where we want to go. We want to find and characterize something like the solar system. So if we want to see and characterize, take a spectrum of an Earth-like planet around a sun-like star, that Earth-like planet is going to be 10 billion times fainter than its star. And that's like a single bioluminescent alga next to that lighthouse. And that's a factor of 10,000 better than we can do today. So understandably, that's too much of a technological jump to do all at once. Oh, and I forgot to mention that not only that, but when we want to look at things that today we see things in the very, very outer reaches of the planetary systems, if we want to find things in more like Earth-like and Jupiter-like orbits, then we need even higher resolution. So now we're not looking halfway across the country, we're looking all the way across the country, or maybe from Europe. And so this is where WEIRST comes in. So WEIRST is the mission that I work on at NASA, JPL. It'll be launching in the mid-2020s, and it will do several different science cases, but in particular, the ones I'm excited about are exoplanet discovery and studies. And as Brandon already mentioned, it will do two different sorts of exoplanet detection methods. It's in the time I have, I don't have enough time to delve into the details about how it will do its microlensing survey, but the punchline is that it will be able to find things like Jupiter, Saturn, Earth, Mars around stars in our own galaxy. It should be able to find a couple hundred things of Earth-sized at various separations from the star. So it'll really flesh out the statistics and our understanding of the populations of planets. But for various reasons, you can never follow up any of these planets in detail. They're going to be found around stars that are much too far away to image directly or to take spectra of. So we'll look at a little bit different population of those and characterize them in more detail with direct imaging. So there'll be two different cameras on this mission, one that will do microlensing and one that will do direct imaging. And so that direct imaging camera will we'll be able to see planets that are 1 billion times fainter than their stars. So not quite all the way to Earth, but something like Jupiter, we should be able to see. So a little small clump of algae next to that lighthouse all the way across the continental US or a little bit farther. And this is in preparation for missions that NASA is considering and working out the details for that might be in the 2030s to look at Earth analogs. So we'll be doing a lot of the technology prep work to go towards an Earth imaging and characterization mission. And at this level, I'm really interested in the technological aspect of all of these detection methods. But for direct imaging with WEIRST, seeing 1 billion to 1 brightness ratio planet means you need incredibly precise instrumentation, incredibly polished optics, but even the best fabrication labs in the world can't make mirrors that are precise enough to give us sharp enough images right out of the factory. So we actually end up making an instrument that can measure its own imperfections and correct for it once it's in orbit. So the way that we do this to both suppress the starlight and to correct for it is shown in this video here. So as the light's coming in, it picks up those imperfections in the optics. The light will be fed to an imaging camera, and you're seeing that image in the upper right. First, I didn't talk about this in detail before, but there are a couple of different pieces of optics that we can put in to block most of the starlight ahead of time. It's easier if you don't even have to put it in your image. But the planet light will pass through because it's separated a little bit, and we'll design those masks so it doesn't suppress the planet light. But all those imperfections in the optics mean that you still have a lot of scattered starlight. So we'll have a mirror that can bend and deform to counteract those optical imperfections that we'll measure once we get into orbit. And so we'll slowly, by looking at the science images and moving that deformable mirror, dig away the remaining starlight so that then we can see the planets in our image, and we can either take an image or a spectrum of those Jupiter analogs. And with that, I will stop and take any questions that you have about WEIRST or direct imaging or anything else.
Thank you. That was fabulous. If people do have questions, please put them in the chat. Turn on your audio line and talk. I'm watching Brandon over here just shake his head in amazement at what we're going to be doing. And
TPL is a fun place to work. I get
Yeah.
to ask. I get to talk to a lot of people working really cool tech.
The technology is astounding to me.
Kevin's asking, what's the launch date for WFIRST?
Mid 2020. So right now the nominal is very late 2025, but I wouldn't say that it's finalized yet. But in the next decade, certainly. So at the moment we're in the process of finalizing the designs for the instrument over the next year or 2 years, and then we start. There's a long period where we have to fabricate it, fully test it, and then integrate the instrument into the telescope, and that the integration and testing part takes several years, in fact, before launch. So we're nearly done with instrument design, and it's just a lot of the fabrication process that will be left starting a couple years from now.
So when you're talking about distances of faraway planets versus nearby planets, what kinds of distances are you talking about in the ballpark?
So there's sort of two separate pieces to that question. There's separations from Earth to those planetary systems. So for the things that we can directly image, those are the nearby ones. So those are usually less than about 300 light years or so is a good rule of thumb, because once they get farther than that, they appear too close to their stars for us to image, even with our very high resolution cameras. The Kepler Space Telescope and microlensing, and to some extent radial velocity, still have sensitivity. They have sensitivity to planetary systems that are close to us, but also to ones that are farther away from us, all within our own galaxy. But within, you can detect planets out with those methods to maybe 1,000 or 2,000 light years from us. And then there's a separate piece of that question, which is close planets, how close a planet is to its star. And so transits and radial velocity are very good at finding things that are in Earth-sized orbits or closer, because they need to see the planet do several orbits around the star for confirmation. So that means you have to be on a short orbit relatively close to your star. We've only been doing these techniques for a few Earth years, so we need things that orbit in an Earth year or less. So that's why we see things that are in Earth-sized orbits and smaller with transits and radial velocity. Direct imaging today is good at finding things that are in orbits that are about 10 times as wide as Earth's and wider, because we just have limited resolution in our images. WFIRST is aiming to find things that are in a Jupiter orbit, so 5 times Earth's orbit and wider. And then the missions that we're kind of conceptualizing right now, spacecraft for the 2030s that NASA might launch, would be aiming to see real Earth analogs, so Earth-sized orbits, Earth-sized planets around nearby stars.
Thank you.
Other questions? All right. Well, let me thank you again, Dr. Bailey. I really appreciate you coming on. That was some very nice stuff that you had to share. And if you don't mind, if we do have any more questions pop up after this, we may send them to you, and hopefully we can post those answers on the Moodle.
Yeah, absolutely. Yeah, thanks so much for having me. I love getting to talk about this stuff. So yeah, thanks very much for the invitation. This is a really cool program.
Yeah, we have a lot of fun with it. So it's about 3 o'clock, so I'm going to wrap this up and let people get back. I believe you guys can see my screen again with that lovely Keck Observatory time lapse. But we have gone through most of the webinars. We only have one more left, 2 weeks from today after Thanksgiving, Wednesday, November 28th. And we will be talking a little bit about finding life, going into characterizing exoplanets and how that relates to finding life. And then we will be opening up the applications for the mini fund. So please be thinking about those projects that you might do. Contribute to the weekly discussion topic that's up there. share some of your ideas. We'll respond. We'll give you some feedback on what sounds great. If there are any ideas we have about how it could work even better. And hopefully you guys can respond to each other's as well. Otherwise, we will see you on November 28th, and we will go ahead and wrap up for today. So thank you very much, everybody.
Thanks for